In this video, I'm going to be talking about a device that I've been working on recently that I think is fairly interesting. Several months ago, I came across an article that discussed a particular Aboriginal tribe that maintains a sort of mental compass, and their language uses cardinal directions heavily in place of relative references such as left or right. This system allows the speakers to navigate accurately across unfamiliar terrain, regardless if it's day or night. The idea of maintaining a mental compass really stuck with me because I have naturally a pretty poor sense of direction. Unfortunately, being able to do this requires, as the author Stephen Levinson puts it, a specialized kind of background computation of orientation and direction. I then had the thought to create an electronic tool that could train the user to maintain a mental compass without requiring any active input, and this is the device that I came up with to solve that challenge. The basic idea of it is pretty simple. Essentially, it involves a belt that the user wears around their chest that indicates roughly towards magnetic north. There are 6 vibrational motors spaced evenly around the belt, and built-in sensors determine which direction the wearer is currently facing and pulses the corresponding motor closest to north. The core component is this LSM3L3 DLHC, which is a triple-axis accelerometer and magnetometer. It uses an I2C serial interface, so it's fairly simple to use an Arduino to read the data from the sensors. This is a simple rig that I made to test the magnetometer. Currently it's running a pretty basic script that just points the LED closest to true north, so you can see more or less the main principle of the device. When I first received the magnetometer, it was pretty much unusable. I was able to improve the accuracy using calibration software from like 2011, and so now it reads a consistent heading that's also tilt compensated, and also it takes into account magnetic declination, not that you can really tell. The website where I found the calibration software will be linked in the description below. There are many resources showing how to perform calibrations, as apparently it's a fairly common issue with these devices. Here you can see a visualization of the accelerometer data before and after calculating 12 unique calibration values based on the errors in hard iron distortions, scale factor, soft iron distortions, and misalignment on each individual axis. For the haptic feedback, I used these little sealed rumble motors. They draw less than 40 milliamps at 3 volts, so I decided to drive them directly from the Arduino pins with a 100 ohm resistor in series, which isn't best practice, but it hasn't caused any issues so far. The whole system is powered by 2 3.7 volt lithium-ion batteries in series that were pulled from old Samsung phones. I used a charge protection circuit to charge these cells. All of the components are stitched onto a belt made from an elastic band, which allows for a small amount of compliance when moving around. Using the device is really straightforward. It's pretty inconspicuous when worn under clothing, and the vibrations are barely perceptible, so it's easy to forget you're even wearing the belt. In terms of efficacy, it seems to work decently well as far as I can tell, though more testing is definitely required to see if it could provide a lasting effect. Overall, it was a pretty fun experiment. Thanks for watching.